Alright, so we're going to be working on programming a 3-2-1 block in MasterCam. Whenever you first launch MasterCam, your window should look something like this. If you want to go to the View tab, you can hit Show Axes and you'll be able to see your axes. You can right click and choose isometric and you can kind of get a feel for your environment. So that's our origin right there. You can also toggle showing the axes by hitting F9. So for our block, we're going to want to start by setting up our stock. So for that, we've got a slightly oversized block, and we're just going to first go to Machine, and we're going to choose Mill, and we'll go with the default mill for our post processor. If those aren't there, you can also go to machine setup whenever you're over there, and if you go to files and then replace, so you can open a file browser. If there's nothing preloaded in that menu, you can go to the default CNC machines. It should launch this folder, and then you'll just need to pick from these two. If there's no other post processors loaded, just go ahead and choose this one. The mm is just the millimeter default, so we'll go with this one, which is the inch. So same thing. Okay, now that we've defined our post processor, we need to define our stock. So we'll expand this tree under properties and go to stock setup, and we're going to do a rectangular stock like this, and our stock dimensions are 2.2 inches wide and 3.125 inches long and 1.5 inches tall. We're going to toggle display on so that we can see it, and we're going to choose solid. While we're at it, we're also going to want to program from the bottom left corner. That's just my preference. You can program to the middle if you want. You can do top right, you could do top left, bottom right, it's up to you. But we're going to do top left, or sorry, bottom left. So we'll choose that corner, and you should see that move to there. We don't need to apply any shift to it, so we'll leave that as a zeros, and we'll just hit OK. And now we've modeled our stock. And so you can zoom in on that and kind of get a feel for it. So we just got a little bit of extra material beyond what we're trying to program. So for something like this, you could create a solid model if you wanted. You could drive it off of the solid model. It's not really necessary, and as far as efficient toolpath motion goes, your best option is going to always be to use the 2D toolpaths with wireframe geometry if that's possible. So if you have straight walled things with square features, round features, contours, if you can use the 2D stuff, it's better than trying to model off of a 3D solid. So for what we're trying to do, we just need to just draw some simple wireframe. So we'll go to the wireframe tab here, and we'll just pick rectangle, and we can adjust our view to the top, and we already know our target dimensions are going to be 3 inches wide and 2 inches tall. So then we are there, and we can just position it however we want. We could just kind of eyeball it, and that would probably be okay, but we can also snap it to the origin and be a little bit more precise with it. So we've now placed our rectangle so we can green check out, and now we have our wireframe. But we need to shift it because we don't want to cut right on the edge if we zero to the corner of our stock, because if the stock curves in a little bit here or something, we may not get a completely machined out wall. So we want to kind of balance the amount of material to be removed on all four sides. So we're going to use transform. You could use dynamic or translate. We'll use translate, that's fine. And then it'll ask you to make a selection. So you can pick a single entity if you want, and it'll highlight, and if you pick it again, it'll deselect it. Because we're working with wireframe, if you hold shift and then pick a piece of wireframe, it will chain everything that it can So if we hold shift and click it, it now selects all of our wireframe. You could also like window select if you wanted to, however you want. But so we select all 4 sides of our rectangle in selection, and then we just need to apply our shift so we can do a little bit of math and determine what centered would be on our stock. So our stock was oversized 1/8 of an inch in X, so we need to shift it by 1/16 of an inch to have it balanced in the X side. So you could figure it out yourself. You can also perform mathematic operations in data entry cells. So you can just type, you could type 1/8/2, or you could type 1/16 or whatever, but then once you hit it, it'll do the calculations for you. So it applies that shift. And then in Y, we were 200 thousandths oversized, so we need to shift by 100 thousandths, so 0.1. And now if you look, our little pink box, which is the translation, looks like it's centered in our stock environment there. We still have the red there, which it means that that's the original, and it's trying to keep the original there, which we don't want to do. If you accidentally did, you could always just select the original and delete it later. But you can also go here, and rather than have it on copy, which is where it's at now, we're going to change it to move, and now the original is gone and we only have the translation. So that looks alright, so we just hit OK, and now it's centered. So our stock origin is here. This is where we're going to set up our work coordinate system, and we're going to try to cut this shape out of it. Now for the 2D milling, because it's not stock aware, we're going to need to define the area that we're trying to remove, which is also it's the same dimensions as our stock basically. So we're gonna go back to wireframe, and we'll draw another rectangle, pick from the origin, and then you can drag it to roughly that size. It really doesn't matter. You could be off by a little bit. We're just giving it a sort of a window, a target area of material to remove. You can kind of arbitrarily place it out here, just somewhere in that region, and then you can manually just correct it later. So we know our stock was 3.125 by 2.2, and that's good. So we've got, this is the area between this wireframe and this wireframe is what we're telling it we want to remove. And then we can go back to isometric, and that makes it make a little bit more sense. So we don't need to remove a whole lot. So now that we've got our stock model and we've got our wireframe set up, we need to go generate a toolpath. So we'll go to toolpaths. To start off with, we're going to want to face it down. So we can select face, and we are in wireframe chaining here. If it's in solid, you're not going to be able to pick the wireframe because it's looking for solid features. So make sure you're in wireframe. And then for the chaining features, you could do different types. You could do partials, you could do single entities, but we want to do a full chain. So we'll leave that option there, and then we'll select our machining area. So we're gonna want to face off this whole piece of stock, so we'll just select that outside rectangle and green check it. So we're going to go to tool, and right now our tool library doesn't have any tools loaded into it. If those have been defined, it makes initially starting a lot easier, but oftentimes this is how it's going to look. So you're going to need to go pick a tool from the standard library. So we'll do select library tool, and that brings up just a generic library of all different types of tools. You can apply filters if you know specifically what type of tool you want, but it's not too hard to just filter by tool name and then scroll to what you want. So we're looking for a 3/8 flat end mill. So we're going to just scroll until we start seeing 3's in the first number. So then we got 3/16, so we need to keep going a little bit more. And here we're at the 3/8, and so we're a 3/8 flat end mill. There we go. So we can double click that. It brings it up, but we need to change the default tool number from 287 because our machine only has 10 tool slots. We need to make it match whatever the machine is at. So it doesn't really matter if it's 1, 4, 9, it doesn't matter. But in our machine, we're going to set it up into tool slot 3. So we just need to make sure that it matches in MasterCam. So we'll type 3 there. When we hit tab, it should change your length offset and diameter offset to match the tool number. So we hit tab, and now that's populated. From there, we need to define our feeds and speeds. So by default, they're you know, there are these random values, but and once the library is set up, you can have the values default to populate with whatever you want, but for now we'll just manually override them. So we need to pick a feed and speed, and there's plenty of references out there that you can use to determine what an appropriate starting point would be. If you have access to one, the machinery's handbook is great. If you don't have access to that, you can usually just, you know, you could Google, you know, carbide in mill speed and feed or something like that, and then yeah, any of these options are probably fine. So you can just pick these free references. Yeah, we're looking for uncoated, so we'll scroll down to here. So in mill speeds and feeds for uncoated carbide. And so you find your material first. We're cutting aluminum, so non-ferrous aluminum alloys. The speed needs to be 500 surface feet per minute, and the feed per tooth needs to be, for a 3/8 end mill, come down to here, 0.0032 inches per tooth. So we'll take those two numbers and go back to MasterCam, and surface footage was 500 surface feet per minute, and feed per tooth 0.0032. Plunge rate, we shouldn't be plunging into any material, so we can go pretty quick with that. We'll say 45. We can enable radial chip thing because we're probably going to do a dynamic toolpath, but if you enable it and it's not going to be a factor, then it doesn't really matter. So you can turn it on or turn it off. It's up to you. For holder, we don't need to define a holder because we shouldn't be anywhere close to gouging in the material or crashing the holder. But if you want to do any sort of accurate simulations later on, or if you're on a more complex part, you're going to want to accurately define your holder and your amount of stick out and your tool, just to give everything that the simulator needs to sort of accurately represent what you can expect to see. So you could pick different holders if you wanted, but it shouldn't matter for this. We do have the ST20 LaVille holders modeled up. So for cut parameters here, you can pick your style. There's a few different options. So zigzag it's just going to go back and forth and back and forth. One way, it'll pick the tool up, go back, and will only ever cut in one direction. So you could expect to be a little bit more uniform that way. One pass only works if you have a cutter that has a diameter greater than your width, which we do not, so that's not going to work. And finally, there's dynamic, so it just tries to maintain constant radial engagement of the tool. It's sort of up to you. It doesn't really matter. It's sort of a situational thing. For this, we'll go with dynamic. It doesn't hurt. So approach distance is fine. Max step over, we can go ahead and set that to, we'll say 35%. So 35% of the tool's total diameter will be engaged at any point in time, or at least that's what the algorithm tries to do. There's a couple of times where it's not going to be able to keep that maintained, but it does its best. Stock to leave on floors, we'll set it to 0. We're just trying to get a flat surface, and we'll establish that as our new Z0. For depth cuts, we'll go ahead and engage that. We shouldn't have to remove too much material because the surface is already pretty flat, but we'll go ahead and leave it at the rough step at 50 thousandths, and for our finish cut, we'll do one at 20 thousandths, should be fine. We don't want to engage keep tool down. It should be fine, but we don't want to risk crashing the tool just to save a couple of seconds, so we'll just leave that. So in linking parameters, this is where we define how deep we're going to go. So for our final depth of where we want to be, we can go to absolute, and you can pick on the model. Right now we only have this one depth, so 0 is fine. For defining our top of stock, we'll say we'll start at, we wanted to make it in 2 passes, so we've got a rough at 50 thousandths and a finish at 20 thousandths, so we'll say we're starting at 70 thousandths, so we should get exactly 2 passes. When defining these values for depth, absolute is just the absolute position in this environment relative to this point right here. Top of stock is the same way. If you're in incremental mode, it's based off of where the wireframe is. So in this case, incremental and absolute would be the same because wireframe is sitting at Z0. But if this wireframe was sitting at the bottom or it was sitting somewhere else, incremental would be from that wireframe. It would not be, it wouldn't be based off of this point here. But when you come to feed plane, retract, and clearance, they essentially stack off of each other. So incremental is no longer based off of the wireframe, it's based off of a distance from these values. So you would define your top of stock, and then incremental 0.2 would just be 0.2 over whatever this one is. Wherever this plane is, it's just 0.2 over that. And then same thing with retract over feed plane. It's incremental is 0.2. But if you go to absolute, then absolute is always just 0.25 in this work environment and relative to this point. So you just be aware of those definitions. And then associative is if you engage that, you can just pick points on a solid model. It doesn't really apply here. You could do it here if you wanted, but there's just not a whole lot going on there. So we'll stick with just absolutes for everything. So that should be fine. You don't need to worry about this screen. For arc and filter tolerance, we don't need to adjust this value, but if you are on, especially if you're using dynamic toolpaths, so dynamic creates a lot of lines. It's trying to constantly recalculate to maintain the radial engagement that you tell it to target. And so movements that look like a straight line will be thousands of lines of command for the machine. And on older machines or cheaper machines, slower machines, a lot of times they can't keep up if it's just being thrown a lot of lines. The LaVille's controller is actually pretty good at keeping up with a lot of points being thrown at it. So that's really not too much of a concern on that front. However, it doesn't have a whole lot of memory. It's like a little over 2 megabytes, which is not a very big NC file. So if in the interest of saving space on your controller so that your program will fit, you may want to apply a tolerance or some sort of filtering. Especially on roughing operations, it's not too critical. You could apply a tolerance. You can tell it it's okay to vary 5 thousandths from the amount, and then the cut tolerance is essentially telling it like, okay, from the commanded drive geometry, it's okay to vary up to 5 thousandths in either direction if that helps you to maintain a better cut. And as far as reducing lines, you'd want to use some of your filtering or your smoothing. So you can enable those by just clicking these, and you can have 1, 2, neither, all of them. We don't really need to apply smoothing. So smoothing is going to be looking for things that are close to being aligned but aren't quite aligned. If it's within the tolerance you allow it, it'll convert a bunch of points into a single smooth line, but that it doesn't defeat the point of dynamic, and like I said, this controller can handle it, so it's not really a concern. And then line arc filtering settings is basically like smoothing is, but for arcs. So if you're making a corner and you have a bunch of small points that look like an arc, as long as they fall within the allowed tolerance, and you can vary how much you're allowing it, and you give it a total, and then you can determine the balance between 2 or 3 or however many you want by just playing with these sliders, or you can punch in hard numbers and all the numbers will adjust themselves automatically. But yeah, as long as it sees a series of lines that fall within the tolerance of an arc, it will convert 5 or 10 or 50 small line movements into a single arc movement, which reduces your NC file, and it also allows your controller to move a little bit smoother. But it is varying some from the drive geometry, so just keep that in mind. So we don't really need to worry about that. We'll leave it at the default, but that is an option. Planes, that's fine. We don't need to mess with those. We do want to activate coolant, so we want to turn flood coolant on, and the rest of these values are fine. We don't really need to worry about that. And so we green check it, and then it generates our toolpath. And as you can see, we've got 2 passes. So the first one should be our roughing, and the last one should be our finishing. And they finish right at the surface, so it should make our stock nice and flat. And we should have a nice flat surface there. If we wanted to represent that in our cam environment, because right now if we ran it, it's not going to show it cutting any material because it's a perfectly flat surface and it's cutting right at that surface, so it's not gonna cut. So in our stock settings, we could shift our Z up by just a tiny bit. We'll shift it up by the 70 thousandths that we shifted that we're removing. So we'll say 0.07, and we'll try that. And now let's see the stock shifted up. And so we'll be able to cut that, so it'll just be more accurately represented in any of our simulations. In fact, we can go ahead and select our toolpath, and if we go to solid verify, it will launch here, and then that should give us an idea of what our facing path is going to look like. So it'll bring up this window, and I can make that a little larger. And so here it just shows, here's our stock, there's our tool, and we can just go ahead and let it run, and there's our roughing and then our finishing. So it just makes the surface flat. That looks right, so we can go ahead and close that. So now that we've got this face nice and flat, we can go ahead and work on our side machining passes. So for that, again, if you can stick with 2D milling for any sort of simple shapes or features, you're going to get the best tool motion, and it's also going to be the easiest for your computer to calculate. So if we expand that, for that we're going to use dynamic mill, and any of the tool paths that have this little letter D, that stands for dynamic motion. So you can use an algorithm in the software that attempts to maintain radial engagement. So a lot of these tool paths, especially in the 2D that are here, they just look at a shape and they'll just use a traditional approach to covering the area. And as you approach corners or something like that, your radial engagement on your tool is going to dramatically vary. When you first engage material, you're going to get a very large spike in radial engagement, and then it will stabilize throughout the cut to whatever you commanded it for your step over. And then as you come to the end, it's going to taper away, and you'll fall off to 0. So the dynamic motion just attempts to engage the tool one time, and then just keep it engaged as long as it can at the commanded radial engagement. So we're going to go use dynamic mill for that, and it's going to open this window, and we're going to define the machining region, the area we want to remove material from. When we'll launch the chaining, we're going to do a full chain on the same outside square there, so we're trying to remove the material within there. Green check. For our machining strategy, we have all this air outside. All of this is free space, and whenever possible, you don't want to machine from inside. So if we selected stay inside, it's going to try to helically enter the material from within. It's going to try to stay within this rectangle at all times. We don't want to do that. We want to come from outside, so we'll specify from outside. And then for our avoidance region, we're going to pick this inner rectangle, so we'll go here, pick that one. We're just telling it to stay out of that area because that's our target geometry. That's what we want our block to ultimately be shaped like. And everything else we don't need to define right now. It's fine. So we can hit preview chains and it'll show us, like, okay, it's removing the area in this red striped, and it is operating within this little bubble that it's generated. So that looks alright. We'll green check it. Go back to tool. We've already defined our tool, so it's already here, so that's nice. However, our speeds and feeds have gone back to their default settings, so we can just populate those again, 500 and 32. Again, we are not plunging into materials, so we can go kind of quick on that, save a little bit of time. And we will engage radial chip thinning. And if you notice, it did change the feed rate some, and that value is dependent on your specified radial step over. It just converts the feed rate to give you your actual commanded chip load, because anything less than 50% radial, you're going to have something that is less than commanded due to radial chip thinning if you're climb milling. Holder shouldn't really matter. Our end mill is longer than this actually. We should probably model that more accurately, but the primary thing is just to make sure we have enough we have enough stick out. So on our end mill we have 1 1/8 inches of flutes, and we're not going to clamp onto the flutes. We're not going to clamp lower to the flutes. So I mean we're going to clamp it at like 1.3 or something. So even though the end mill doesn't show that the flutes go up to here, they do. The main thing is just make sure that the holder doesn't crash into the top surface of here, which we only need to go 1 inch down to get our 1 inch on our 1, 2, 3 block. So that shouldn't be a concern. We're not worried about that at this point. That's just because I changed the stick out here. It's asking if I want to update the tool and holder. It doesn't really matter, but yeah, we can say go ahead and update it and everything because this toolpath uses the same tool. It recognizes that, and it's asking if we want to transfer these changes into that one. So we'll say sure. It doesn't really matter. It's not going to affect the toolpath. We're not doing anything stock aware, but if you wanted, you could tell it for the 2D toolpaths. The stock aware motions just look for they just look for the area that was covered by previous operations. It's not like on the 3D where you can actually point to a stock model. It's not really necessary on this because our stock model is represented by our outer rectangle here, and we're not too concerned about over engaging anything. So we'll leave that deselected. Under cut parameters, we want to leave it on climb milling. There's really no reason to do conventional milling. Zigzag saves you a little bit of time in some situations, but we're not really concerned about that, so we'll leave it on climb. For approach distance, we could add a little bit, but we're pretty confident in our measurements of our stock, and we've already added just a little bit of extra on our definition of it, so we don't really need to do that. First pass offset is going to feed off of the outside. So when you're first engaging the material, if you mismeasured your stock a little bit, you may over engage before it's had a chance to finish its first pass. So you can just tell it how much extra you want to leave, and then you can also override the feed rate just for that first pass, and then you can have it pick up again once it's established a safe area to cut in. So we'll leave those at 0. Again, we're confident in how we've modeled our stock against what we're actually working with. On step over, we are going to want to take a small radial step over with a relatively long axial step down. So for our step over, we'll leave it at say 10% of the tool, and then it automatically calculates there. We can also just enter a value of how much we wanted to step over, and then that would correct it here. For minimum toolpath radius, it's not going to affect what we're working with here, but in certain situations, like if it was trying to machine a pocket kind of like this, you can see it highlights these little loops because it'll make a pass and then it'll cut back, and every time it enters and exits the cut, it has to loop in these little radiuses, and you're telling it what the minimum acceptable size is. So if you're trying to get features that are like here, it gets pretty tight. And if you have too big of a radius defined, it's not going to be able to drive the tool in without violating that radius, so it'll stop. And so it may machine it like up to here, and then it would just quit. Even though the tool can fit into here, it quits trying to feed into here, and that's because your minimum toolpath radius is too large. So if you try reducing that value, you tell it it's okay to create smaller radiuses if it needs to go through and do areas like this. But we'll leave it at 10 for this type of path. We're not gonna. It shouldn't really affect it. Gap size is just going to define where it needs to pick up. Again, on this toolpath, it's not really going to matter. But if for something like this, you're just telling it how big of a transition does it need to make before it picks the tool up and rapids, rather than just micro retracting and moving the tool in that way. So we'll leave that alone. It doesn't really matter. The micro lift is going to be for everything that every time it does a transition and it doesn't pick the tool up in rapid, it's going to use a micro lift, so it's going to pick up by 10 thousandths of an inch, and then your back feed rate is going to be how much it moves. So it doesn't rapid in linking moves, but it's a fed motion, but you define the feed rate here. It shouldn't be cutting, so you want to bump it up to something pretty quick, because otherwise you'll spend quite a bit of time in these transitions, and there's no reason that they couldn't move faster. So we'll put it at like 499 or something. Stock to leave on floors needs to be set to 0, because we want well, actually we'll go ahead and cut a little deeper than we want, because we want to have a little bit of extra material. So we're going to tell it to cut to 1 inch, but we want to have a little bit of extra material to work with, so that when we face it off, we can, we don't have to aim for right at 1 inch, because if we do, we might be left with like a thin little ribbon of material on the bottom. And so to avoid that, we'll tell it we want to take negative 0.02. We'll take 20 thousandths extra. Doesn't need to be much. And for stock to leave on the walls, we don't want to finish the walls with 2D dynamic motion. Any dynamic toolpath is a roughing motion. You don't want to finish with those, because like I said, anything like something that looks like a straight line is actually a series of hundreds or thousands of small lines with variance between them. So you'll see the tool moving what looks like along the x-axis or the y-axis, but it's actually moving slightly as it moves along, and you don't want that. To finish it, you want to use a proper contour that will tell it, like if it's a straight line like what we're working with here, it's 4 straight lines, it should be moving in a single like straight line. So your movement command on your controller should be 1 line until it gets from here to here, and dynamic motion is not going to give that to you. So we'll leave a little bit of stock. We'll leave, say, 15 thousandths, just enough for a contour to come back and clean it up. And we'll move on. We don't need to worry about that. Depth cuts we do want to establish, because we don't want to take it all at once. This machine's not rigid enough, and the tool's not going to be able to handle it. We'll save the finishing for the contour. And the only downside to doing depth cuts is you get these sort of blend lines at every point where the tool moves, down to a new lower low. You get horizontal lines on your part. But because we're going to clean it up with a contour, it doesn't really matter. So we'll just do this to keep the load on the tool and the machine under something that's more manageable than trying to engage it all at once. So the max rough step we'll define. We're trying to go down 1 inch total, so we'll try to take it in 3 passes. So we'll tell it we're actually doing 1.02 inches because we're leaving that negative stock to leave. So we'll tell it 1.02, and then we'll just divide it by 3 and let it figure it out. So it does the calculations for you. So that's our max rough step. We don't need to worry about a finish step in depth, because that's not really what we're concerned about. So we'll leave that at 0. And we'll move on to the next step. Entry motion only matters if you're helixing, or you can do different types of path. You can do profile, you can do medial. It shouldn't matter. All of these don't, it's never going to enter the material. It's always going to start from the outside and work in. So it doesn't matter what we define on here. It's not going to change anything. Don't need to worry about breakthrough. And for linking parameters, we're back here. We're going to work in absolute again, just because that's pretty safe. So for our absolute depth, in the first tool path, we cut down from 0.07 to 0. So our new top of stock is 0. And our overall depth we're aiming for is minus 1 inch. And it's going to add the negative stock to leave independent of this value. So we don't need to do that. If we ever wanted to change our depth, we'd probably better off leaving this here and then just playing with the stock to leave. So we'll leave that. Don't need to worry about these. We won't worry about filtering. Planes are fine, and coolant, just make sure flood is on, and then that should be good. So we'll green check and let it generate, and there we go. So we've got our same tool motion in 3 step down, so 1, 2, 3, to get to our final target depth, which is just over 1 inch. And if we want to back plot it, we can. Just let it run. It just gives you an idea of what it's going to look like. And these little loopy moves like that right there where it comes back, those are those micro lifts where it picks the tool up just a little bit and it it doesn't wrap it, it moves at a fed rate or a feed rate, but it's a really fast feed rate. So if you kind of look, you can see the micro lifts where it picks up and then moves. And then this lower level is our actual commanded cut depth. So that looks good. You can green check that, and if we want to go and solid verify that, we can. If you are picking things in the tree here, if you have this setting enabled, it's going to turn on only the toolpath that's selected. If you want to toggle the view for it, you can press that, and whatever is selected will be viewable. If you want to select multiple, you can use Control to select additional items, and then if you also hold Control, you can select to deselect individual items without changing everything. If you're not holding any of the keys down and you pick one thing, it's only going to select that one thing, and it's going to deselect everything else. And then kind of like with the File Explorer, if you have something selected and you hold Shift, there's only two things, so it's kind of hard to see, but if you hold Shift and you select something else, everything between those two, you know, the beginning and the end, will be selected. So if we Shift or Control select these, we'll select both. If we want to toggle the view of them, we can toggle it here. We can also enable this setting, and because these are selected, it's going to show them. We select both because we want to watch both operations, and then we can go to solid verify again, and we can watch it run both operations, so what we've programmed so far. So there it does the facing, it does the finishing on the facing, and then it comes and it cuts the sides. And there we go. So getting pretty close, but as you can see, kind of, yeah, you can see these little ridges here are because it's, you know, that goes back to, you don't want to use dynamic motion as a finishing move because it's not perfect. It's not what you actually want it to be. So that's why you want to leave a little bit of stock and then clean it up with a proper contour later. So we'll go back to here and we'll do that last operation, which is just a contour. Again, it's a 2D thing. We're only working out of here. We don't have a solid, so we're not going to work with the other types of toolpaths. Now, for the other ones, it didn't matter. For this one, the direction of the arrow that pops up whenever you are chaining matters, because that defines the direction the tool travels. And we're trying to pick this inner rectangle because that's our drive geometry, that's our target geometry we're trying to clean up. And whichever line you choose is going to be the line that it starts on. And if you take that line segment, so say we focus on this line segment here, if you divide that in half, like at this point, if you click anywhere on this side of that half, so this half of the line, it's going to position the beginning of that line segment at this side, and it's going to send it the other direction. It's going to send it away. So if we're here and I click on this half, it's going to place the contour beginning here and sending it that way. So if we here, I click here, see the arrow is here, and it's sending it that way. If for whatever reason I had picked it, if I didn't want it to go that direction, I wanted it to go the other direction, I could either clear it and reselect it. So say I could select the other side. I could also just flip the direction of the arrow, so I could hit here and reverse it, and then you see the arrow changes direction. That's important for determining whether you're climb milling or conventional milling, because the machine doesn't know. In a contour or any of these dumb toolpaths, it doesn't know if it's climb milling or conventional milling. It's just traveling along the direction of the contour that you tell it to. So because we're compensating to the left, the tool cuts on the left side because we want to climb mill, so the tool's rotating in a clockwise motion like this as it moves. We want it to compensate to the left, and we want the tool to travel this direction, so we cut the material here. So this arrow direction is correct for what we're trying to do. So we go ahead and green check that. Tool, using the same tool. Again, the surface footage has changed, so 500. We can rapid retract, that's fine. You could also put a really big number there. That's just how fast it picks the tool up between links. Plunge rate, again, we're not plunging in the material, so we can go 45 is fine. Feed per tooth was 32 thousandths per tooth. And Go back to our holder, that's fine. We know we have enough flute stick out. The simulation may suggest otherwise. It may say that this is a gouge because we haven't defined the flutes as being long enough to make the cut, but we know that the actual end mill that we're working with is long enough. So it's good practice to model this, but it's not necessary in this case. Cut parameters, we'll leave computer comp on. We're just doing a simple 2D contour. For our compensation direction, like I said, we want it to compensate left. If we compensate right, it's going to climb mill, and we don't want that. Or sorry, it's going to conventional mill, and we don't want to do that. We want to leave it at the default, which is compensate left. Tip comp is fine. Don't need to worry about any of these. Stock to leave on walls, we're going to leave it 0 because this is our finishing operation. Stock to leave on floors, we don't want to. We want to leave some negative stock because we want to have a little bit of extra material to work with, like what we did in the previous operation. But we don't want to have it driving along the floor because it might kind of drag the tip when it's in the cut, and that might lead to a little bit of deflection. On a more rigid machine or a bigger tool, it probably wouldn't matter so much. But we already cut 20 thousandths extra stock on the first operation, so we can go ahead and just add. We'll give it back. We'll use negative stock, but we won't go 20 thousandths. We'll maybe go minus 15 thousandths. So a little bit of negative stock, but not all the way. No depth cuts. We're trying to make this in one pass because this is a finishing operation. Lead in, lead out, we will enable because it helps the tool from, rather than just plunging straight into the material, it offsets it and then allows it to kind of ramp in and then ramp out. So tangent is good. We have plenty of room, so we don't need to worry about it. You might start playing with the length of the lead in. You may play with the diameter, or the arc radius that it takes on the lead in, or maybe the degrees of sweep, like how much of a sweep it takes. You can play with all of these things if you need to in tighter situations where you run the risk of gouging your part somewhere else. But in this case, we have plenty of room, so we'll just leave it at the default. We do want to add a bit of overlap. That just allows it to stop slightly farther than it started, so that we get a nice clean wall at the beginning and end point. So we'll add 50 thousandths of overlap. We don't need to play with the adjustments here, so we can move through. No breakthrough. You could do multiple passes if you wanted, so you could have it step in. We're only taking 15 thousandths. We don't really need to do that. So we'll leave that. We're not doing tabs. And for linking, again, we'll use the same values we used in the previous operation. So we'll go all absolute. And for our depth, we're doing -1 inch. And our top of stock. It doesn't really matter because we're doing it in one pass, but this is where it's going to feed from. So the feed downward is defined there. Actually, the feed down is going to start at the feed plane, sorry, but the top of stock is going to be how it calculates depth cuts. But like I said, we're not doing depth cuts, so it really shouldn't matter. But to keep things consistent, we'll just tell it it's at 0. That doesn't matter. We don't need to apply any sort of filtering on this one. That's fine. And finally, we got coolant, and just turn that on. So we'll hit green, and there's our simple contour. So it comes in at the 0.2 mark. It starts to feed down. The green motion is an entry motion. The red motion's a lead out, and then the yellows are retract in a rapid retract. So it comes down, it feeds in, it arcs in, and it goes around the part one time, and then it arcs out, and then it retracts, and then we should have our target geometry. If you would have gotten the chain wrong, that looks correct. So if we were to back plot that and let it run, we're trying to just go around the outside of the part, ignoring that the tool isn't modeled to have enough flutes. It looks right. Our geometry is right. The tool is right. The edge of the tool is right on that inner box that we're trying to cut. So that looks correct. If you would have gotten the geometry wrong, if your arrow was the wrong way, you can go in here and you can hit reverse from here, and you can notice that the arrow direction will change. So if we reverse that And then if we regenerated it, see, now yeah, so now it's compensating in the wrong way. So if we backplot it, it's still compensating left, but it's now cutting in the wrong direction. It's conventional milling. So the tool is always rotating in a clockwise method, but rather than climbing through the material, it's conventional milling. So it's sort of ramping into the material, which we don't want. It tends to lead to chatter, and we don't get a radial chip thinning effect, and it increases tool wear. So try to avoid that. You always want the tool rotating in a clockwise method, and then biting the material and climbing through it. You imagine the flutes biting in, and then the direction of the feed is in the direction that we want it to be. So we'll go and change that back. So just reverse, and okay. And if for whatever reason you had your cutter comp the wrong side, so if you had it on the right side and you generate that, it's now cutting on the inside of the box, which is wrong. We're not trying to do that. So just always be aware of the direction your tool's traveling in these tool paths. You can't just tell it, I want to climb mill, and then expect the computer to figure it out for you. You have to specify your chaining directions. So that's pretty much it. If we go and do one final verify, we should be good to go. But so it faces, then it roughs. That looks good, and then it does a final contour, which is already finished. But and then we get our target geometry. We can toggle our wireframe off and our gnomon if we want to be able to just see the block. But that's pretty much what we're going for. And then for op 2, we'd flip it over. We'd flip it over, put it back in the vise like this, and then we'll just face that off, and we'll get our, this is already defining a flat surface that is perpendicular to these planes. And this plane is 3 inches long, and then this one is 2 inches long. And then all we have to do is flip it over and machine this off, and just go down enough to give us our 1 inch that we're looking for, and then we'll have our finished 3-2-1 block. So now that we've got all that figured out, we can just go ahead and post it. So we're going to select, make sure all of our toolpaths are selected. You can do that by just selecting this group, or you could individually pick them. So you can do control, like I was saying, with these you can hold control and you can select and deselect them as you go. You can also do the shift select. So we got one selected there. If we hold shift and then hit 3, now they're all selected between that range. So however you want to do it, select the toolpath you want to export, and then we hit this little G1 to post the operations. This is just asking about the post-processing. We just leave it at the default, hit the green check. It asks where you want to write the file to. We can write it to a desktop, or we could write it straight to our USB flash drive, however you want to do it. We're going to need to transfer this file to the machine via a flash drive. So you can write it somewhere in your documents. You could save it to a folder. You can write it straight to the USB. However you want to do it. It's just standard file manipulation. For the name, it defaults to t.nc. We can change it to, we'll call it 123 block, and then this is op 1, so we'll say op 1, and that looks fine. So yeah, we'll write it to the, yeah, we actually have an old op 123 block op 1, so it should ask if we want to overwrite it, but we'll say sure. So we'll hit save. It says, this file already exists, you want to replace it. We'll say sure. So it posts it out. Give it a second to launch Code Expert. So that brings up the code. So like I said, the dynamic paths have a lot of lines. They generate a bunch of lines for things that look pretty much like straight motion. But that looks fine. We've got our normal G28 go home. We've got M30, so the whole program looks correct. We do need to give it a unique O number here. So if it's the same O number, which 4 zeros is gonna be on the machine, We want to give it something that's not already on the machine. Otherwise, it will give you errors when you try to load them. When you try to load the file to the machine, it's going to say that program number is already taken. So we'll tell it something random. We'll say, I don't know, 48. And it doesn't matter on this machine because it does have an A-axis, but if you're using a default post processor and you're trying to post to like a 3-axis HOS and you don't have like an actual HOS post processor, the default works pretty well, but it does try to post A-axis moves, so it'll say A0. We're not using rotary axes in this toolpath, but it just sort of defaults to commanding them. Some machines don't care, they'll just ignore it, but the HOSes for sure are going to complain about this A0. When you try to run it, it's going to read up to this line and then it's going to throw an alarm and say the A-axis is disabled. So if you're on a HOS, you're going to want to just select it and delete it. Like I said, on this machine it does have an A-axis and it doesn't matter, so we could leave it, we can delete it, it doesn't matter. But so if you delete it, you need to delete it at every operation. So if you scroll down, there's going to be one at the end, and then if you're not sure if you got them all, you can go to the home tab and then hit find, and you could just type the letter A and then hit find next, and it's going to find up here in some of these commands, it'll show some, but throughout the program, yeah, so it loops there, so there is no more left in the program, it's just looping, so that's fine. All of these parentheses things are just comments. The machine's not gonna, anything within the parentheses is just ignored by the post processor or by the controller. It's just meant for the operator to be able to read. So there's no more A's, so this would work on a HOS now. And we do need to remember to hit save, because anytime you manipulate a line, it gets a little yellow box on it, and it's just letting you know that you've changed that line, but it hasn't been saved. Same thing with the little asterisk there. It's letting you know that the file's been changed, but it has not been saved yet. So you need to remember to save it. When you hit save, the asterisk goes away, and you got little green boxes that just show like it was, successfully manipulated. Same thing down here, the green box. So that's good. The file is ready to go. We can go ahead and close Code Expert. And if we wanted to, save our MasterCam file, you're going to want to save often. Sometimes MasterCam has been known to crash, so just be sure you save your file as you go, any chance you remember. And if you go to your desktop, you can find the program that you wrote. So we got 123blockop1.nc. It's just a text file. It's an NC file, but you can open it with a text editor, so you can open it with Notepad, and you've got the same text. And if you wanted to manipulate it, you could. But just make sure you've got this unique O number, and yeah, you should be good to go. So we'll throw it on a flash drive and go over to the machine and get that all set up and ready to run. Alright, so back in our CAM environment, we're going to work on operation 2, where we just need to face down the 1, 2, 3 block until we get our final desired thickness. So we've got our stock kind of modeled here. It's not entirely accurate, but for what we're doing, we really just need the rough dimensions of our block, which is modeled here. So we're going to use a facing toolpath again, so we'll come to 2D and pick face. We've got our wireframe already drawn up, so we'll select that. Go back, pick our 3/8 flat end mill again. Our settings are not set, so we can go into our tool, and when you're building your library out, you can define your feeds and speeds. So here we've got just default settings, and if you want, we can tell it that our default surface feed per minute for aluminum is 500, and our feed per tooth is 0032. Make sure that your number of flutes matches, because that's how it does the calculation for your feed rate. If you have say it thinks you have a 4 flute end mill and you really have a 2, now your feed rate is going to change it's going to be off by a factor of 2. So make sure that you've got that correct. And you can define material properties, you can define the name, the tool codes, all those things if you want. But for what we need it's just nice to have these settings set. So once those are there, you can also define tool geometry, so your amount of stick out. Again, for what we're doing, doesn't really matter. But if you want accurate simulations and be able to tell if you're going to have tool collisions or holder collisions, or if stickout's going to be an issue, you need to have this modeled properly. And then if you start using stock aware functions that will check to make sure that there's no holder collisions and make alterations to the toolpath to avoid them, then that for sure needs to be modeled, as well as your holder. So we'll leave that for now. And once we've made those changes, you see the values changed automatically. If they didn't change and you want to update them, you can right click on the tool and then you can click reinitialize feeds and speeds, and then that would reset it to whatever the save settings for the tool are. We're going to enable radial chip thinning, and we'll move on to the next step. Like I said, holder doesn't really matter for what we're doing here, but in more advanced operations and things where you need to have awareness of the holder and you need to be able to accurately simulate, you need to model your holder appropriately. And for our cut style, we're going to stick with the dynamic. We could try a different path if we wanted to, or we could even rough it with dynamic, and then if we want a certain surface finish, like if we wanted parallel lines or something, we could do a zigzag or a one pass, or sorry, a one way. But it's really up to you. So we're going to go with dynamic. For step over, we'll stick with 35%. All of that is okay. We want to climb mill. We want to leave 0 stock, and we want to enable depth cuts. 50 thousandths is probably, that's fine. We'll go a little lighter on the finish pass. We'll do one at we'll say 20 thousandths. We want it to pick the tool up. It should be fine, but it's a one-off part. We don't need to try to save a couple of seconds and accidentally crash our tool, so we'll leave that. Back in our linking parameters, by facing the stock down in the previous operation, we know exactly where our now new top of stock is that we just measured from, and so we can just reset that Z height as our work coordinate Z height. So that's now going to be 0, and we just need to go down by the depth of basically how much we want to remove. So our stock measured out at 1.486, so we just need to take off 0.4860 inches. So we'll go to absolute, tell it we want to go to minus 0.486, and feed plane and retractor okay. Filtering is fine. We didn't have any issues with lines before. That's fine. Coolant, we want flood coolant, and pretty much everything else should be good to go. So we'll hit OK, and it'll generate, and there's our toolpath, which looks about right. If you imagine this is our original total thickness of the block, about 1.5. We're going down 0.48, so about a third of that. That looks correct. And if we want to go ahead and backplot it, we can just get an idea of the motion, but I mean it should be the same facing operation that we had from the first path, and then it's just stacked until we get to final depth. So that looks good. So we'll go ahead and post it out. We can just drop it on the desktop. We'll name it 123 block op 2. That's fine. And here we go. So looks fine. We do need to give it a unique O number, so we'll tell it, I don't know, 84. Sure. Save it. The bar turns green, so it's committed. And we can go ahead and close the code expert. And for transferring this program, we'll use the program transfer tool instead of using a USB. It's a little bit more convenient. So if you're on this desktop that's in the APL currently, it may change in the future, but this desktop is connected directly to the LaVille CNC via an Ethernet cable, so you can transfer programs between the two, and that's really all you need, is just an Ethernet connection. Yeah, so go launch program transfer tool there, and it connects. Make sure the mill is on. If it's not on, you won't establish a connection, but we've got it here, so that's good. And you can navigate through the through folders with this sort of tree system if you want. You can also just use the graphical window. So we'll go and access the LaVille first, so it loads the memory setup right now. So we've got a few subfolders and paths. There's not a ton of memory, so typically most of these are empty because it periodically gets cleaned out just to free up what little bit of space is available. But we'll go into my folder, and there's some older programs there. I'm not sure what they are. We'll go ahead and delete them. I think program 48 is active, so it's probably not going to let us delete it, but we can command it anyways. It just won't delete it. So we select them all and hit delete, and it asks, are you sure you want to delete them? You can hit yes. It goes through and deletes them, and we get an error. It rejected the deletion of the active program. So yeah, 00048, which was the active program, did not get deleted. 7 were deleted, and that one is the only one remaining. So we can minimize this, and we can find our new program we just created somewhere, wherever it is. Where is that thing? Oh, there it is. So put it here. Hopefully your desktop's a little bit more organized than mine. So like I said, you can use the graphical window, so or you can navigate through the PC here. But once you find the folder or the file you want to drop, make sure it has a unique O number. If it has an O number that's already being used by something in the system, you're gonna get an error. And if it is larger than the system can handle, you'll get an error for a memory overrun. So you can take your folder, you can take your file, and you can just drag and drop it into whatever directory you want to on the machine. So we'll just let it go here and hit download, and it'll take a second depending on file size. Dynamic toolpaths tend to produce way more lines, so they're going to take longer to transfer, and you're going to have more issues with getting everything to fit on the machine. But if you get this message, one program has been downloaded and it doesn't say anything about memory, then you should be good to go. If it is larger than the available memory, it will still download the program to it. You'll see it'll look like it's successful. You can access it on the machine, but at the point that it ran out of memory, it'll just stop writing lines. So if you go to run the program, it will probably run fine right up until it gets to where it ran out of memory, and then it quit writing the program to the machine, and then it'll just stop moving. It runs out of commands, and I don't even think it alarms out. The machine just kind of sits there because it's waiting for its next command. So just be aware, if you get a memory thing, you don't just dismiss it. It may look fine, but you're going to need to clean it up, make your file smaller, clear up some memory, something. So now that we've got that file successfully loaded up on the machine, we can go ahead and run it, and we don't need to worry about any of the messing with the USB and changing devices and anything like that. So let's go do that.